Assalamu alaikum, students and friends. It feels great to have you back to Sir K Lab's physics and chemistry tutorials for high school students. This episode focuses on two problems involving conservation of mechanical energy or the transformation of kinetic energy to potential energy, which is either gravitational potential energy, elastic potential energy, or both. So stick around till the end of this video, watch and learn. The questions are: number one, a glider of mass 0.240 kg is on a frictionless horizontal track attached to a horizontal spring of force constant 6.00 Newton per meter. Initially, the spring, whose other end is fixed, is stretched by 0.100 meter, and the attached glider is moving at 0.400 meters per second in the direction that causes the spring to stretch further. Question letter A: what is the total mechanical energy? That is, kinetic energy plus elastic potential energy of the system. Question letter B: when the glider comes momentarily to rest, by what distance is the spring stretched? Question number 2. A 3.00 kilogram fish is attached to the lower end of a vertical spring that has a negligible mass and with a force constant K equals 900 Newton per meter. The spring initially is neither stretched nor compressed. The fish is released from rest. Question letter A: what is its speed after it has reached 0.0500 meters from its initial position? Question letter B: what is the maximum speed of the fish as it descends? Problem number 1 describes a glider with a mass m equals 0.240 kilogram on a frictionless horizontal track attached to a horizontal spring of force constant K equals 6.00 Newton per meter. Initially, the spring, whose other end is fixed, is stretched by 0.100 meters. So that is the value of x sub naught or x naught. And the glider is moving at an initial speed v naught equal to 0.400 meter per second to the right, okay, in our figure here. All right, so for letter A, or question letter A, we are asked to find the total mechanical energy. That is, the kinetic energy plus the elastic potential energy of the system. And the total mechanical energy of the system is denoted here by capital E, while the elastic potential energy is denoted by capital U sub E, and of course, Ke refers to the kinetic energy of the glider. All right? Now, in question letter B, we are asked, by what distance delta x is the string stretched when the glider comes momentarily to rest? Or, that is, when the final speed v is equal to 0. So, to be able to compute the total mechanical energy, we use the formula for the elastic potential energy denoted by capital U sub E. Alright? That is equal to 1 half the product of the force constant K and the change in the horizontal distance, or delta x squared. Sometimes we call this the elongation, the change in length, delta x. Also, the change in the kinetic energy, right, delta Ke equal to 1 half the mass times the square of the initial speed v naught. So, when the glider is momentarily at rest, all right, the total mechanical energy, capital E, is purely elastic potential energy, right? So, the total mechanical energy, E, is just equal to the elastic potential energy, or 1 half K delta X squared, right? So, when we isolate delta X squared from this equation, we'll be getting the square root of both sides of the equation. We get the working formula that we need for finding delta x. That is, delta x is equal to the square root of twice the value of the total mechanical energy, all right, divided by the force constant K. Moving on to our computations for problem number 1, starting with the elastic potential energy of the spring, all right, that is denoted by capital U sub E, equal to 1 half K delta X squared, right? So, when we substitute the given quantities, we have um, U sub E, or the elastic potential energy of the spring, equals 1 half times 6.00 Newton per meter, and to be multiplied by the square of delta x, 0.100 meter. So doing our math, we get the elastic potential energy U sub E equal to 3.00 raised to the negative 2 power joules. That's in 3 significant figures. Likewise, the change in kinetic energy, delta Ke, all right, using the formula 1 half the mass times the square of the initial speed v naught, or substituting the quantities, we have 1 half multiplied by 0.240 kilogram and multiplied by the square of v naught, 0.400 meter per second. So again, when we do our math, we get the value for delta Ke equals 1.92 raised to the negative 2 power joules. Take note, the final kinetic energy when the glider momentarily stops is equal to 0, right? So the change in the kinetic energy, right, if you notice, is just the result of computing for the kinetic energy when the uh, glider was still moving at its initial speed, all right, at x not equal to 0.100 meter, or with an initial speed of 0.400 meters per second, right? So, our answer to question letter A, therefore, that is getting the total mechanical energy of the system, denoted here by capital E, which is just the sum of the elastic potential energy and the kinetic energy that we just computed here, all right? Or that is capital E equals 3.00 times 10 to the negative 2 joules plus 1.92 times 10 to the negative 2 joules for a total of 4.92 raised to the negative 2 joules as the total mechanical energy of the system. I pointed out earlier that when the glider momentarily comes to rest, all of its mechanical energy is in the form of elastic potential energy, since the final kinetic energy is zero. So, this total mechanical energy, capital E, equal to 4.92 times 10 to the negative 2 power joules, is equated here to 1 half K delta X squared. So, for us to finally compute delta X, all right, this is in answer to question letter B. All right. So when isolated, delta X will become equal to the square root of twice the elastic potential energy. All right. Over the force constant K. All right. So this comes out as a result of deriving the formula from here. All right. So when you isolate delta X, this is what comes out. So when we substitute, we have the value of the delta X equals square root of 2 times 4.92 raised to the negative 2 power joules, and that's divided by 6.00 Newton per meter. All right. Take note, all these quantities are inside the radical sign. All right. So with the help of your calculator, we find the value of delta X equal to 0.128 meters in three significant figures. Alright, this is the distance by which the glider slides before momentarily coming to rest. Okay, starting from x naught equals 0.100 meters. For problem number 2, we are given the mass of the fish equal to 3.00 kilogram, and the fish is attached to the lower end of a vertical spring that has a negligible mass. Okay, the spring has a force constant K equals 900 Newton per meter. It is understood that the higher end of the spring is firmly fixed to any rigid body. The spring initially is neither stretched nor compressed. So our target variables are the speed v of the fish, all right, when its displacement y is equal to 0 or negative 0.0500 meters, right? This is negative because relative to the chosen reference level, which is position 1, all right, y sub 1 is assumed to be equal to 0. All right. Um, Take note that the fish is released from rest. All right. So the displacement delta y, which is negative 0.0500 meter, is measured from the reference level, hence the negative sign. All right. The other target variable is the maximum speed Bmax. All right. That is the maximum speed of the fish as it descends or moves down. All right. Take note that when the fish is released, all right, two forces are acting on the fish. All right, such as the force of gravity or its own weight and the force of the spring. All right. Now, in answering the questions, all right, both questions A and B, we must realize that at position 1, the fish is at rest. So its initial kinetic energy, of course, is equal to 0. Its gravitational potential energy, capital U sub G, is also 0 because we choose the reference level as position 1. All right. And at that position 1, denoted by y sub 1 equals 0, it's understood that the gravitational potential energy must be equal to 0. The elastic potential energy, capital U sub E, must also be equal to 0. The fact that initially uh, the spring is neither stretched nor compressed, right? So the total mechanical energy of the system, therefore, is equal to 0 at position 1. All right. Now, at position 2, okay, when the fish has been displaced, all right, uh, by negative 0.0500 meter, all right, the fish now has all the three forms of mechanical energy. It has kinetic energy, potential energy, both elastic and gravitational, all right? But the total of these three forms of energy is still equal to 0 in accordance with the law of conservation of mechanical energy, all right? So at position 2, the kinetic energy of the fish is expressed as 1/2 of its mass times the square of its speed, all right, at position y equals negative 0.0500 meter, while its gravitational potential energy, of course, is the product of its mass and acceleration due to gravity and the position y sub 2, all right? And lastly, the elastic potential energy U sub E is also expressed as 1/2 of its what we call force constant, the force constant of the spring K, and the square of the position y sub 2. Take note that in both equations for the potential energy, y sub 2 is defined as the delta y, or the change in position, all right, when the fish is displaced by 0.0500 meters below the reference, all right, at position number 1. Moving on to our computations, the gravitational potential energy, capital U sub G, of the fish at y sub 2 equal to negative 0.0500 meters can be computed, all right, by just multiplying the mass, acceleration due to gravity, and the position y sub 2, or 3.00 kilogram times 9.8 meters per second squared times negative 0.0500 meters. So when we do our math, we get the value of the gravitational potential energy of the fish at that position y sub 2 equal to negative 1.47 joules. So as expected, it is negative, or it has a negative sign because the gravitational potential energy is being measured, all right, below the relative, below the what you call reference level, all right. The reference level that we chose is position number 1, where y sub 1 naught is equal to 0. So similarly, the elastic potential energy of the fish at the same position, all right, capital U sub E, or 1 half k y sub 2 squared, that is 1 half times the value of k, 900 newtons per meter, and multiplied by the square of the value of y sub 2, negative 0.0500 meters. So again, doing our math, we get the value for the elastic potential energy, capital U sub E, equal to 1.13 joules, also in 3 significant figures. From the energy conservation equation, which was presented earlier, all right, the kinetic energy of the fish at position 2, when added to the gravitational potential energy and the elastic potential energy, will have their sum being equal to 0, right? Or kinetic energy, which is 1 half mv squared, all right, can be equated to mg y sub 2 minus 1 half k y sub 2 squared. So we just isolated the kinetic energy by transposing both the elastic and the potential energies to the right side of the equation. And since what we want is the value of the speed b, all right? So when we isolate and get the square root of v squared, we get v equals square root of 2 times 1.47 joules. This is the value of the gravitational potential energy minus 1.13 joules, which is the elastic potential energy, all right? And to be divided by the mass of the fish, 3.00 kilogram. With the help of your calculator, we get the value of the speed of the fish at a position number 2 equal to 0.480 meters per second. For question letter B, we are looking for the maximum speed of the fish as it descends, right? But unfortunately, we are not given the position or the vertical position where the maximum speed is acquired, all right? Uh, so there is a need for us to apply the law of equilibrium, all right? The law of equilibrium, which states that the net force acting on the fish, all right, so that it has a what we call maximum speed or velocity, all right, the net force acting on the fish must be equal to 0. Alright? So, that happens if the gravitational force exerted on the fish, in other words, when its weight balances the force exerted by the spring. Alright? So that is the meaning of this simple equation. The weight of the fish has the same magnitude as the spring force, denoted by F sub E. Alright? They are equal in magnitude but opposite in direction. So, when this condition is satisfied, we say that the body or the fish is in state of equilibrium. Alright? Dynamic equilibrium. So, since the weight is the mass times acceleration due to gravity, and the spring force F sub E can be expressed as the product of the force constant K and the displacement Y sub 3. Alright? And our target variable at this point is the position Y sub 3. So isolating Y sub 3, we get this working formula. Y sub 3 equal to mg divided by K. That is, the mass of the fish, which is 3.00 kilogram, times acceleration due to gravity, 9.8 meters per second squared, and divided by the force constant, 900 Newton per meter. So again, doing our math, we get the value of the position Y sub 3 equal to negative 0.0327 meters in three significant figures. It has a negative sign because, again, the displacement Y sub 3 is understood to be below the reference level. Why not? Why not being equal to 0? Right? So, knowing now that the position where the fish has the maximum speed, okay, the position Y sub 3 equal to 0.0327 meters below the reference level. And if you notice, all right, this position Y sub 3 is or has a lower magnitude compared to Y sub 2, right? Earlier, uh, we were given the value of Y sub 2 being equal to negative 0.05 meters. That's below the initial position. So, this means that Y sub 3 is a point within the path of the motion of the fish. That is closer to the initial position. Alright? Which means that the fish already acquires its maximum speed, okay, even before reaching position 2. Alright? So, we can infer that at position 2, alright, where y is equal to negative 0.0500 meter, we say that the fish is already slowing down, right? Earlier, we got the instantaneous speed at y sub 2 being equal to 0.480 meters per second. Right? So that is not the maximum speed of the fish. In fact, that is less than the maximum speed, which gives us the idea that when the body or the fish has reached position 2, it has already passed position y sub 3. Alright? Now, the energy conservation equation presented earlier can also be written as ky sub 3 squared. Alright? Originally, this is 1 half ky sub 3 squared minus 2 mgy sub 3. Originally, that's just mgy sub 3. And mb squared originally is 1 half mb squared. Alright? But to get rid of the numerical coefficient 1 half, so we multiplied, okay, all terms by 2. Alright? That's how we got this. Alright? 1 half is multiplied by 2, so it becomes 1. And for mgy sub 3, it has now a numerical coefficient of 2. Alright? 1 half of mb squared has also been cancelled. Alright? And of course, that's still equal to 0 in accordance with the law of conservation of energy. Right? Now, we will determine the value of each of these terms. For ky sub 3 squared, that is simply the product of the force constant, 900 Newton per meter, and the square of y sub 3, negative 0.0327 meters. Or, ky sub 3 squared has a value of 0.962 joules, also in 3 significant figures. We assume that the force constant has 3 significant digits. Likewise, for the term 2 mgy sub 3, that value, or that has a value equal to 2 times 3.00 kilogram multiplied by 9.8 meter per second squared, and then multiplied also by negative 0.0327 meters. Or 2 mgy sub 3 has a value equal to negative 1.923 joules. Right? So from this energy conservation equation, we can express mb max squared as 3.00 kilogram multiplied by V max squared. Alright? So, when we substitute, or when mv max squared is isolated from this original equation, mb max squared becomes, or is equal to 2 mgy of 3 minus k y sub 3 squared. Alright? So, in isolating mb max squared, we just transpose ky sub 3 to ky sub 3 squared and negative 2 mgy sub 3 to the right side of the equation. Alright? That's why we got mb max squared equals 2 mgy sub 3 minus ky sub 3 squared. And substituting, alright, where mb max squared is equal to 3.00 kilogram times b max squared equal to 2 mgy sub 3 earlier obtained as 1.923 joules minus ky sub 3 squared, also determined earlier equal to 0.962 joules. Simplifying, alright, we isolate Bmax squared and then getting the square root of both sides of the equation, Vmax becomes equal to square root of 0.961 joules divided by 3.00 kilograms. That is equal to the square root of 0.320 meters squared per second squared. With the help of your calculator, we finally get the value for the Vmax equal to 0.566 meters per second in three significant figures. Alright? So, this is the maximum speed of the fish as it descends, alright, to the position y sub 3. So that concludes my lecture tutorial for this topic. Hope to be with you in the next episode. Mabuhay. MashaAllah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.